Let's do a couple other examples that illustrate the concept of implicit differentiation. We see an equation here, the third root of y plus x squared times y squared equals 9. That is an equation involving x and y. We can use implicit differentiation to find the y prime. Let's go ahead and do that. The first thing I'll want to do is rewrite the third root of y into exponential form as y to the 1/3, and then plus x squared, y squared equals 9. Then I can take a derivative of both sides. Once I do that, I have to realize that y is this function. So taking a derivative of y to the 1/3, I would get 1/3 y to the 2/3. And then multiply times the derivative of the inside function, which is y prime. In order to take the derivative of the x squared, y squared piece, I'll have to use a product rule. So derivative of x squared is 2x times normal y squared plus normal x squared multiplied times the derivative of y squared, which will be 2y to the first multiplied times the derivative of the inside function, which is y squared. On the right-hand side, I get 0. Now I go through the same steps that I've done a number of times before. I'll get all of the terms without a y prime on the right side and all of the terms with a y prime on the left side. The easiest way to do that in this case is to subtract 2xy squared from the left-hand side and then subtract 2xy squared from the right-hand side as well. At this point, I can factor out a y prime on the left-hand side. So let me do that. Negative 2xy squared will stay on the right-hand side. Now I can easily solve for y prime by dividing the negative 2xy squared by this expression in my parentheses. So I'm going to end up with the fraction negative 2xy squared divided by the quantity 1/3 y to the 2/3 plus 2x squared y. And if we had a point, we could find the slope of the tangent line or the instantaneous rate of change at any point which satisfies this equation. Now, the other trick that I wanted to demonstrate is using implicit differentiation when we have an equation like this. Square root of y plus 9x y squared equals 12. So the key here is that this y squared in the denominator is going to be tough to deal with. I can deal with that utilizing a quotient rule, but it might be more effective if I simply multiplied both sides by y squared in order to rewrite the equation before I take derivatives on both sides. Let's go ahead and do that. So again, before I'm taking derivatives, I'm going to rewrite. So I'm going to multiply the left-hand side by y squared. And then I'm going to multiply the right-hand side by y squared as well. Remember, the square root of y is the same as y to the 1/2. So if I multiply y squared by square root of y, I get a y to the 2.5 power, or to the 5/2 power, or 2.5 power. If I multiply the y squared times 9x divided by y squared, I just end up with 9x. And on the right-hand side, I have 12y squared. Notice taking derivatives of both sides now is going to be a lot easier than dealing with taking derivatives of my original equation. So let's go ahead and do that. When I take a derivative of the left-hand side, I'll get 2.5 y to the 1.5 times derivative of the inside function, which is y prime. When I take the derivative of 9x, I just get 9. When I take the derivative of 12y squared, I get 24y to the first multiplied times the derivative of the inside function. The inside piece is y, so that is y prime. There's a couple of options of moving things around. What I'm going to do is I'm going to subtract 2.5 y to the 1.5 times y prime from both sides. And what that's going to end up doing is leaving the 9 on the left-hand side, 24y times y prime, minus 2.5 y to the 1.5 times y prime is going to be on the right. Now I can solve by factoring out a y prime. That equation becomes 9 is equal to 24y minus 2.5 y to the 1.5 power, all multiplied by y prime there on the right-hand side of my equation. And so y prime here will simply be 9 divided by this coefficient, 24y minus 2.5y to the 1.5 power. One thing you do have to be slightly aware of when you multiply both sides by a y squared is we are assuming that y is not 0. Because if y squared was 0, then this 9x over y squared would not be defined. But there's the derivative, as you can see. I would like you all to use implicit differentiation to find y prime for this equation here. So what's the instantaneous rate of change at a certain point for this equation you see on the screen? Push pause on the video and I'll explain this in the next video.